December 3rd, 1942. Warren, Michigan. The production floor of the Detroit Arsenal tank plant stretched 5 city blocks long, a cathedral of steel and concrete echoing with the thunder of rivet guns and the grinding scream of metal against metal. Frank Kowalski, a 34-year-old machinist from Hamtramck, with grease under his fingernails and doubt in his eyes, stood before the welding station, where M4 Sherman tank hulls moved past at their maddeningly slow pace. In the pocket of his work overalls sat a crumpled piece of paper covered in pencil sketches, a solution to a problem that the engineers upstairs had already dismissed twice as impractical. The assembly line crawled forward. Each tank hull required hours of careful welding, positioning, and inspection. The quota seemed impossible. Washington demanded more tanks. The boys in North Africa needed more tanks. But the laws of physics and time seemed insurmountable. What Frank Kowalski didn't know, what none of the 5,000 workers sweating through double shifts could have known, was that within weeks, his rejected idea would trigger a cascade of innovations that would transform American tank production from an engineering marvel into something approaching industrial magic. The crisis had begun 18 months earlier, in June 1940, when General Motors President William Knudsen made a telephone call that would reshape American industrial history. On the other end of the line sat K.T. Keller, the unflappable president of Chrysler Corporation. Knudsen's question was direct. Could Chrysler build tanks for the United States Army? Keller's response became legendary in Detroit industrial circles. "I don't know," he admitted with characteristic honesty. "I've never seen one of these things." But within hours, Keller had assembled a team. Within days, that team had traveled to Washington, examined prototypes in Illinois, and begun studying 186 pounds of blueprints. By June 1940, the United States Army owned exactly 66 medium tanks. Nazi Germany's panzer divisions had just torn through France with thousands of armoured vehicles, demonstrating a brutal new form of warfare that made America's military preparedness look pathetically inadequate. President Franklin Roosevelt understood what was coming. Even before Pearl Harbor, he recognized that the arsenal of democracy would need to outproduce the Axis powers by margins that seemed mathematically absurd. On August 28, 1940, Chrysler received its first contract to build 1,000 M3 medium tanks. The government purchased 113 acres of farmland 17 miles northeast of Detroit, in an area that would later become the city of Warren. Construction began in October 1940, during Michigan's brutal winter, on what would become the Detroit Arsenal tank plant. The architect was Albert Kahn, the German-born genius who had revolutionized factory design through his work with Ford and other automotive giants. In 1937, his firm had been responsible for 19% of all architect-designed industrial buildings in the United States. By 1941, he would design 20 million square feet of defense plants. The arsenal he designed for Chrysler embodied his philosophy that architecture was 90% business and 10% art. The main building stretched 5 city blocks deep and 2 blocks wide, with 3-foot-thick concrete walls designed to withstand bombardment. Massive overhead cranes could lift entire tank sections and transport them along assembly lines that snaked through the cavernous interior. Frank Kowalski was among the first wave of workers hired in early 1941. He had started at Dodge, Maine in 1929, working his way from the paint shop to tool and die work, developing an instinctive understanding of how metal behaved under stress. The transition from automobiles to armored vehicles proved more difficult than anyone anticipated. A civilian car contained approximately 15,000 parts. The M3 medium tank contained twice that number, with tolerances measured in thousandths of an inch. In January 1941, with the building still under construction, Chrysler engineers and workers began mock-assembling the first tanks in sections of the plant where walls hadn't yet been erected. The winter was savage. Heating systems couldn't be installed until more of the structure was complete, so management brought in a steam locomotive and parked it inside the partial factory, using its boiler to keep workers from freezing. April 24, 1941, marked a milestone that seemed almost miraculous. Less than 8 months after breaking ground, the Detroit Arsenal delivered its first completed M3 medium tank to the United States Army. The ceremony was broadcast over nationwide radio. 5,000 people gathered to watch as the 30-ton steel monster rolled off the assembly line. The tank fired its weapons, smashed through telephone poles, and demolished a mock-up house. But behind the ceremony, the production numbers told a sobering story. 1 tank completed in April, 6 more in July. Production was measured in units per month when the War Department needed hundreds per week. Frank Kowalski worked the night shift, 6 p.m. to 6 a.m., 6 days a week. He was assigned to Station 12, where hull sections came together for final assembly. The traditional method involved positioning two massive sections with cranes, clamping them with dozens of fixtures, and having teams of welders work around the perimeter. Each M3 tank required approximately 180 hours of labor to complete. By December 7th, 1941, when Japanese bombs fell on Pearl Harbor, every production target doubled, then doubled again. Roosevelt set goals that seemed divorced from physical reality. 100,000 tanks, 200,000 aircraft. At the Detroit Arsenal, the crisis came in June 1942, when Chrysler received orders to convert production to the new M4 Sherman tank. Engineering estimates suggested each M4 would require 200 hours of labor, potentially reducing monthly production just when the military was screaming for more output. Frank Kowalski studied the M4 hull assemblies with the practiced eye of a man who had spent 15 years watching metal move through factories. The problem wasn't the complexity of the design. The problem was the assembly sequence. The rejected idea came to him during a lunch break in late October 1942. Instead of building two complete half sections and joining them, why not build the hull from the bottom up in progressive stages? The bottom plate could be positioned once and never moved. Side plates could be added and welded while supported by that base. The whole process could happen at one station rather than requiring multiple crane movements. He sketched his ideas and dropped them in the suggestion box that Chrysler had installed near the plant entrance. 2 weeks later, a production supervisor named Jim Hendricks pulled him aside. "Kowalski, we looked at your hull assembly idea. Engineering says it won't work. The thermal stresses from welding would cause the base plate to warp. The fixture would be too complex and expensive to manufacture." Frank nodded and went back to his station. But the rejection gnawed at him. Over the next 2 weeks, working on his own time, he refined his concept. He borrowed engineering textbooks from the Detroit Public Library. He made cardboard models at his kitchen table. He created detailed sketches addressing each objection the engineers had raised. In early November, he submitted his revised proposal with calculations, thermal distribution patterns, and specific fixture designs. Another 2 weeks passed. Then Hendricks pulled him aside again. "Kowalski, engineering reviewed your second submission. They say the calculations are overly optimistic. The fixture design would require specialized tooling that would take months. And even if it worked, the time savings don't justify the risk. If your method failed and we lost a week of production, that's 30 or 40 tanks that don't reach the battlefield." But December 1942 brought a crisis that would change everything. On December 7th, exactly 1 year after Pearl Harbor, the Arsenal's production numbers were reviewed by a visiting delegation from the War Production Board. The current production rate was still running at approximately 60 tanks per month. In North Africa, Operation Torch had just begun, and tank losses were brutal. The War Production Board representative spent 3 days walking the production floor with a stopwatch and clipboard. His report identified Station 12 as the critical constraint. Everything upstream could produce components faster than Station 12 could assemble them. The entire production line was limited by the speed of hull assembly. The report landed on KT, Keller's desk on December 10th, along with a directive from William Knudsen. "Fix the hull assembly bottleneck, or we'll bring in an outside consulting firm." Jim Hendricks, the supervisor who had twice rejected Frank's idea, sat in the emergency meeting with a sick feeling. After the meeting, he pulled Frank's 2 rejected proposals and read them again. The ideas were actually sophisticated. That evening, he took the proposals to Carl Brun, the chief production engineer. Brun read through Frank's work without speaking. Finally, he looked up. "Where did this come from?" "Floor machinist named Kowalski. Submitted it twice. We rejected it both times." Brun was quiet for a long moment. The difference between a good engineer and a great one is knowing when someone without credentials might be right. "Get Kowalski up here tomorrow morning. We're going to prototype this." December 12th, 1942. Frank Kowalski walked into a conference room filled with men in white shirts and ties. Carl Brun extended his hand. "Mr. Kowalski, I've read your proposals. I think you're onto something. We're going to build a prototype fixture and test your assembly sequence. Can you do that?" Over the next week, He worked 16-hour days in the prototype area, where engineers and machinists collaborated. The fixture evolved through multiple iterations. On December 18th, they ran the first test. 4 hours after starting, they had a completed hull assembly. Conventional methods required 7 hours. The results exceeded even Brun's optimistic expectations. The hull was completed in significantly less time, and the weld quality was actually superior. On December 21st, K.T. Keller himself came to the production floor to inspect the prototype hull and review the test data. He understood both the technical details and the cultural implications. A floor worker had solved a problem that had stumped engineers. Keller made a decision that would reshape the plant's culture. Put it into production. Start with one station. If it works as promised, we'll replicate it across all hull assembly positions. And I want Kowalski's name on the procedure documentation. Over Christmas week 1942, the Station 12 team worked around the clock implementing the new method. January 1943 brought validation. The single station using Frank's method was completing hulls in 4.5 hours, a time reduction of nearly 40%. By the end of January, management decided to replicate the new method across all hull assembly stations. The faster hull production meant Station 12 was no longer the bottleneck. Now, turret assembly became the constraint. The turret team, inspired by Frank's success, proposed their own innovations. They redesigned fixtures, revised component installation sequences, and implemented parallel operations. Turret assembly time dropped by 25%. Then final assembly became the bottleneck. The team there redesigned tool carts, created visual aids, and implemented what would later be called just-in-time delivery. Final assembly time dropped by 15%. The most profound change wasn't technical. It was cultural. Workers throughout the plant began paying attention to their processes and submitting suggestions. The suggestion box overflowed with proposals. Management assigned engineers to work with workers to evaluate ideas. February 1943 brought measurable impact. The arsenal completed 87 Sherman tanks. March saw 103. April broke through to 130. May brought welding technique innovations. June saw paint process improvements. July introduced a redesigned transmission installation method. By August 1943, the plant was producing 175 tanks per month, more than double the rate from 8 months earlier. But the breakthrough came in October 1943 with what became known as the Kowalski weld sequence. Frank noticed that heat from early welds caused metal expansion affecting later welds. He proposed a symmetrical welding pattern that would distribute heat evenly. The engineering team worked with Frank and senior welders to design the pattern. By November, they had a welding pattern that reduced thermal distortion by 60%. The Kowalski weld sequence was implemented across all welding stations and shared with other tank plants nationwide. November 1943 brought another milestone. President Roosevelt and First Lady Eleanor Roosevelt visited the Detroit arsenal. That month, the arsenal produced 217 Sherman tanks. By December 1942, exactly 1 year after the crisis, the arsenal reached its peak wartime production record. In that single month, with 5,000 workers operating 3 shifts daily, the plant completed 896 Sherman tanks. 896 tanks in 31 days worked out to approximately 29 tanks every single day. More than 1 tank per hour during production hours. The production time per tank had been cut to approximately 35 hours of labor, less than 1/5 the time required when production began. The Detroit arsenal alone produced 22,234 tanks during World War II, approximately 1/4 of total American tank production. That single facility outproduced the entire German tank industry. Germany manufactured approximately 45,000 armored fighting vehicles during the entire war. The Detroit arsenal, one factory in Warren, Michigan, built half that number. In total, American factories produced 89,568 tanks between 1941 and 1945, dwarfing Axis production. The Sherman tank became symbolic of American production philosophy. German tanks like the Panther and Tiger were arguably superior individually. Panthers required 150,000 man-hours to manufacture. Tigers took more than 300,000 man-hours. German production never exceeded 19 tanks per day across all factories. The Sherman was designed for mass production. It was mechanically reliable, easy to repair, and available in overwhelming numbers. The war ended in August 1945. The arsenal's tank production immediately ceased, but the facility continued operating after the war. During the Korean War, the plant manufactured 3,443 Patton tanks between 1952 and 1954. In the 1960s, it produced M60 tanks. During the 1973 Arab-Israeli War, the arsenal ramped up to produce 5 tanks daily. In 1979, it began producing components for the M1 Abrams. In 1982, Chrysler sold its defense division to General Dynamics. The last tank rolled off the line in 1996, ending 55 years of armored vehicle manufacturing. Over that span, the facility produced more than 60,000 tanks. Today, portions of the original site have been redeveloped for civilian use. The U.S. Army maintains a presence there, with the Tank Automotive and Armaments Command still headquartered at the location. A Michigan historical marker commemorates the arsenal's role, noting the record production of 896 tanks in December 1942 and the plant's total wartime output. The lesson extends far beyond manufacturing. It speaks to fundamental questions about innovation and where good ideas come from. How many transformative innovations are dismissed because they come from unexpected sources? The engineers who initially rejected the suggestion weren't incompetent. They were applying legitimate concerns about risk. What changed was the crisis becoming severe enough that established methods were no longer adequate. The War Production Board's report created urgency that overcame institutional inertia. The partnership that emerged represented the ideal of collaborative problem-solving. The engineer brought theoretical knowledge and authority to implement changes. The machinist brought intimate knowledge of the production process and creative insight. Neither could have achieved the breakthrough alone. The multiplication of innovation throughout the arsenal showed how cultural change could be more powerful than any individual technical improvement. Dozens of incremental innovations combined to transform the entire production system, cutting production time from 180 hours per tank to 35 hours. Those additional tanks translated directly into tactical and strategic advantages. More armor meant commanders could accept losses knowing replacements were flowing at rates the enemy couldn't match. Germany maintained a focus on engineering excellence that undermined their production capacity. German tanks were superbly engineered but complex and expensive. They never solved the manufacturing problem. German military culture valued technical excellence. American industrial culture valued efficiency and production volume. In total war fought across multiple continents, the American approach proved decisive. The arsenal of democracy wasn't just about having more factories. It was about having a system that could identify problems, implement solutions, and continuously improve at a pace that overwhelmed enemies. The story of how one rejected idea cut tank production time in half is ultimately about that system. It's about institutions willing to admit they didn't have all the answers. It's about engineers who could recognize valuable insights from unexpected sources. It's about workers empowered to think critically and contribute solutions. The suggestion box at the Detroit Arsenal represented something profound about human creativity and organizational effectiveness. Every person possesses knowledge developed through unique experiences. The engineer knows things the machinist doesn't, but the machinist knows things the engineer doesn't. The question is whether organizations can create environments where different kinds of knowledge can interact and produce innovations greater than any individual could achieve alone. December 1942, when the rejected idea was finally taken seriously, marked a turning point in understanding how organizations could leverage collective intelligence. The 896 tanks produced that month stood as testament to what became achievable when institutional humility met individual insight, when practical knowledge partnered with theoretical training, when crisis created urgency to question established methods. The rejected idea wasn't rejected because it was flawed. It was rejected because it challenged assumptions, came from an unexpected source, and required taking risks when safety seemed paramount. The crisis made risk-taking necessary. Success validated the approach. The cultural transformation proved more valuable than any individual innovation. The tanks that rolled off that assembly line carried American soldiers across Europe, supported liberation of concentration camps, helped end the Nazi regime's attempt to remake the world through conquest. Each tank represented hundreds of hours of labor, thousands of parts, and the cumulative wisdom of workers and engineers collaborating to solve problems neither could have solved alone. Somewhere in the mechanical heart of each one was the innovation that, building from the bottom up, could cut assembly time dramatically. The insight that welding patterns could manage thermal distribution, the recognition that incremental improvements could combine to produce revolutionary results. The mathematics of victory were written in many forms. Strategic planning, tactical innovation, cryptographic breakthroughs, scientific advances all played crucial roles, but perhaps nowhere were equations more straightforward than in industrial production. More tanks arriving faster than the enemy could destroy them, produced by workers who understood their contributions mattered, that their ideas had value, that the distance between factory floor and victory was measured in production hours reduced, in quality improved, in problems solved through collaboration. The rejected idea became part of that equation. Not the largest part, not the most celebrated, but essential nonetheless. A reminder that victory comes not just from grand strategy, but from countless small improvements. Not just from brilliant generals, but from thoughtful workers. Not just from accepting established methods, but from questioning them when circumstances demand better solutions. The arsenal stands today as a memorial to that principle. The tanks are gone, rolled away to museums or scrapyards decades ago. The workers who built them have passed into history. But the lesson remains, inscribed not in marble or bronze, but in the enduring recognition that innovation comes from unexpected places, that rejected ideas sometimes prove correct, and that cutting production time in half starts with someone willing to suggest there might be a better way, and someone else willing to listen.